The table below gives the marks obtained by 10 students taking a maths test and a physics test. Both tests are marked out of 50. So one student scored 40 in maths, 43 in physics, 43 in maths, 46 in physics, 28 in maths, 32 in physics, and so on. Part 1, draw a scatter graph for the data. So we're going to plot our points using dots on our scatter graph. The x-axis represents the maths marks and goes up as far as 50, and the y-axis represents the physics marks and goes up as far as 50. Notice that the maths axis starts at 25. This is because if we have a look at our maths marks, 28 is the lowest mark, and if we have a look at our physics axis, 30 is the lowest value on our physics axis, and 32 is the lowest physics mark. So it doesn't actually have to start at 0, 0. So the first one's been done for us, and this represents 28 on the maths axis. It's around 28, and 32 on the physics axis. So we can cross that off, we've used it. So next I'm going to plot 40 on the maths axis, 43 on the physics axis. So 40 on the maths axis is here, and 43 on the physics axis is around here. So I'm going to plot my point. So next is 43, 46, and then 49, 47, and 34, 39, and 31, 36, and 32, 38, and 40, 45, and 38, 43, and finally 39, 42. So part 2 says, is there a correlation between the two sets? The points are reasonably close to a straight line. So we can see the points are reasonably close together. So we can say that a correlation exists between the sets. Say that a student who scores highly in maths will definitely score highly in physics. We can only conclude that, in general, the better you are at maths, the more likely you are to do well in physics. So this graph has positive correlation because our data values are going uphill, and it is quite strong as well. They are quite close together. So we could even say it's strong to moderate or moderate to strong positive correlation. At the end of a marathon, 8 athletes are randomly selected. All of the athletes are asked to give their age and their time in minutes for the race. The results are given in the table below. So the first athlete was 33 years of age and his time was 132.6 minutes. The next athlete was also 33 years of age and his time was 132.1 minutes. The next athlete was 31 years of age and their time was 133.1 minutes, and so on. Part 1, draw a scatter graph of the data. So the first athlete was 33 years of age and his time was 132.6. So we're going to go to our x-axis, which represents age, and notice that the lowest value was 24 because the youngest person in our list was 25, so we don't need to go down to 0. And it doesn't go above 34 because 33 was the oldest person in our list. And likewise with the time, it starts at 132 because the shortest time was 132.1, and it stops at 135 because 134.6 was our longest time. So it doesn't need to go down to 0 on our time, which is our y-axis either. So So the first person is 33 years of age. So 33 is here on our age axis. And their time was 132.6, which is around here on our time axis. Next we have 33 and 132.1. Next we have 31 and 133.1. Next we have 26 and 134.0. Next we have 26 and 134.1. Next we have 25 and 134.6. Next we have 30 and 133. And finally 29 and 133.5. So part 2 says, what is the type of correlation between the two sets of data? So we can clearly see that our data values are all very close together. So our dots are all very close together. So first of all, we have strong correlation. And we can also see that our dots are going downhill, they're going downwards. So we have negative correlation. So the type of correlation is strong negative correlation. Part 3, describe the correlation between age, which is our x-axis, and time, which is our y-axis. So as age increases, the times in general decrease. Part 4, explain why the correlation described in Part 3 will not apply for athletes in the 54 to 64 age bracket. In the 54 to 64 age bracket, one would expect marathon times to increase as athletes got older. In the 24 to 34 age bracket, times improve as the athletes get older, as marathon athletes generally achieve their best times in their early 30s. Therefore, it is important that we are careful when making predictions that are outside the range of the sample data.